This is the third in a series of 6 videos which try to explain something of the Higgs field and the way in which it can give mass to the known elementary particles of nature. Someone who has studied mathematics and physics to around the age of 20, or who is reasonably familiar with most of the ideas shown here, should be able to work through the arguments presented in the 6 videos so that they have some grasp of the sophisticated concepts involved without having cut too many corners. A lot of new ideas will need to be introduced, and although these are no more difficult than the concepts shown here, they will require a good deal of work if they are to build up to a coherent understanding of the Higgs mechanism and to try and understand what's really going on. This is part 3, in which we will try to apply the Lagrangian method to fields, and in particular to the scalar field. As we explore this further, it should lead to an understanding, eventually, of the Higgs mechanism. In parts 1 and 2, we discussed something of the standard model, which describes the behavior of the known particles to great accuracy. However, the model predicts that they should all be massless. In particular, we showed how that gauge invariance requires that the gauge bosons, the force particles of the standard model, all have zero mass. In practice, however, 2 of those gauge bosons, or 3, the 2 W's and the Z, were seen to have quite large masses, and it was stated that this was because of the Higgs field. In order to explore this, we delved into some very simple Lagrangian mathematics as it applied to a simple classical mechanical system. Create the Lagrangian from kinetic energy minus potential energy, and then apply Euler's equation to it. We then said that this method could be applied to the quantum fields of the particles of the standard model, and we came to the following conclusions. The Lagrangian must deal with energy per unit volume of space-time, and it is to be called a Lagrangian density. Using the example of a simple scalar field phi, we showed that the potential energy per unit volume will vary as phi squared, and we wrote it as potential energy density equals phi squared over 2. We also illustrated that the kinetic energy per unit volume of the scalar field phi will contain 4 terms: d phi by dt squared minus d phi by dx squared minus d phi by dy squared minus d phi by dz squared. And in order to save space, this differential of 4 terms will be written as 1 in the shorthand form d mu phi all squared, where this mu is an index running from 0 to 3 for time, x, y and z. 0 for time, 1, 2 and 3 for x, y and z. So given these 2 facts, that the potential energy per unit volume for a field is some constant times phi squared, and the kinetic energy per unit volume depends on this 4-term differential, it should not seem unreasonable to you that I suggest that the expression for the Lagrangian density of a scalar field, which is kinetic energy minus potential energy, could be written like this: L equals a half d mu phi squared minus a half mc squared over h bar all squared times phi squared. There's the kinetic energy of the field, the sum of the squares of the 4 differentials, and there's the potential energy, some constant times the field squared. Never mind the reason for those constants. It's usual in this kind of physics anyway to use units of measurement that make the velocity of light c equal to 1 and Planck's constant h bar also equal to 1, just as we suggested for the permittivity of free space epsilon naught, that was made equal to 1 earlier. Also in these equations, we usually write the mass of the excited particle as mu rather than m. This means that my equation for the Lagrangian density of a scalar field phi can now be written as L equals a half d mu phi squared minus a half mu squared phi squared. This equation, written in some way or other, will be one of the starting points for thinking about using Lagrangian mathematics on a scalar field, the Higgs field, in order to try to make sense of it. Now at this point I ought to apologize that, like many textbooks, I have used mu for two entirely different things in the same equation. The mu in the derivative is an index running from 0 to 3, indicating that there are 4 terms in the derivative: time, x, y, and z. The mu in the multiplier of phi squared is definitely not the same thing. It's actually the mass of any excited particle from the field, equivalent to the m in the other versions of the Lagrangian. I apologize for that, but it is standard practice to work with those letters. Okay, so that's the Lagrangian, or the Lagrangian density of our scalar field. If you remember, when we looked at classical mechanics, we said that once you've got the Lagrangian, you could apply Euler's equation in order to get the equations of motion of the system. In that particular case, the system related to distance changing with time. It was a simple mechanics system, and Euler's equation was d by dt of dl by dx dot equals dl by dx. Now we're talking about fields instead of distances, and space-time instead of time. Then Euler's equation can't be what it was. Instead of being d by dt dl by dx dot equals dl by dx, it becomes, now wait for it, d mu of dl by d of d mu phi equals dl by d phi. Now that might look a lot more complicated, but if you'll just spend a moment and think about it, it just has phi instead of x and 4 x mu's instead of time. You need to spend a moment looking at this to believe that this is not that complicated. In other words, the derivative by time is now a derivative by time, x, y, and z. That's the d mu. The differential of L with velocity, which dl by dx dot, is now dl by d of the derivative of the field with time and space, a bit like the x dot was dx by dt. Think about it, it makes sense. The right hand side is easy to match up. We've just changed x for phi. We now need to apply this Euler's equation to our simple scalar field Lagrangian if we're going to get what you might call the equation of motion of this very simple field, scalar field. Believe me, this isn't difficult to do. You just take Euler's equation, put in this value of L, and do the various differentiations. I won't show it line by line. I'll just say that what you end up with is this equation: d2 of mu phi minus mu squared phi equals 0. Now that should remind you of what we had with the spring mass system. d2x by dt squared minus omega squared x equals 0. Remember that x has been replaced by the field phi, and time has been replaced by space-time, 4 things. In other words, the equation of motion, if I can use that phrase, of this simple scalar Lagrangian will be something like the equation of motion of simple harmonic motion. The field, if you like, will wobble, or rather oscillate, if disturbed, just like the spring oscillated when it was disturbed. Once again, you can think of the motion of the field, if I can use that word motion when talking about a field which is changing, you can think of it as being a bit like a ball rolling in a U-shaped potential cup or potential well. If the sign of phi squared in the Lagrangian is negative, as it is here, then the system is perfectly straightforward. The cup is curved upwards, the field in stable equilibrium, and any disturbance will make the field oscillate. There will be energy involved in the oscillation, as the field increases and decreases, and the disturbance, wave, particle, whatever you like to call it, will have a mass. It will be a real mass, and the mass will be given by mu. If for any reason that multiplier in the equation was 0, the mass term of the Lagrangian would disappear, and the Lagrangian would be L equals a half d mu phi all squared. In that case, we would obviously have a massless particle. No potential energy would be involved if the field were to change in some way, and this is a bit like a ball rolling on a flat surface. This would just have the derivative term in the Lagrangian. The field could still be excited, there could still be a wave or a particle generated, but as the field changed or oscillated, the ball wouldn't go up and down in potential energy. There'd be no potential energy involved, and hence the particle would be massless. Also, if for some reason, we'll see later, the mass mu could somehow be imaginary, then this would make mu squared itself negative. Having two negatives in the equation would mean that we would have a positive phi squared term in the Lagrangian, and it would be very strange. It would be a bit like a ball on the top of a hill. Somehow the field would be unstable, but we'll go into a bit more of that later. So this equation is the basics of the Higgs field Lagrangian. But there's one more thing. The Higgs field is called a free field because it has no sources, no kinds of charges from which it emanates or ends up. And I don't just mean electrical charges. It's scalar because it has no direction. However, the fact that it is self-sourcing means that it also interacts with itself. We talked earlier about self-interaction terms in Feynman diagrams, and in discussing this field Lagrangian, we ought also to consider that there will be some kind of self-interactions within the field. It turns out that these self-interactions will give an extra kind of potential energy to the field. Now, it's difficult to give a meaningful classical explanation of this. My best shot would be to think of a magnetic field, which of course is a vector field. We know that if there were another magnetic field nearby, there would be forces involved between them, and so there'd be extra energy in certain situations. Well, somehow a free field like the Higgs field can affect itself and have an extra energy from that self-interaction. I'd like to be able to make an analogy with self-induction in a magnetic field, but that would be stretching it too far. Suffice to say, the potential energy of a free scalar field doesn't just depend on phi squared, as I had argued earlier. It has to have what we call a quartic term in it as well, a term with the field to the power 4. The quartic term means that the field somehow interacts with itself. So at last, here's my final take on the Lagrangian density of a free scalar field like the Higgs, where I've modified the potential energy to include a negative quartic term. It's positive inside this bracket here, but it's a negative quartic term. L equals a half d mu phi squared minus a half mu squared phi squared plus a quarter lambda phi to the 4th. Close that bracket. We've got the kinetic term with the field changing with time and distance, the straightforward potential term where the field is stretching over time with distance, and we've got this self-interaction term making even more potential energy. To be honest, we can often ignore this self-interaction term in considering the basics of how fields will behave, but we won't get rid of it right away because sometimes it contributes in ways that we can't ignore, in fact in crucial ways, but more of that later. Just to reiterate, phi is the scalar field, and phi is just a number, just a real number. At least it is at this stage, although there's more to come later. We'll say more about that later. The field phi appears in the kinetic energy term on the left as the derivative squared. So the way the field changes with position and time will be important. And the mu in that part of Lagrangian has 4 values, 0, 1, 2 and 3. to do with time, x, y, and z. And there are really 4 terms in the equation, which I'm writing here as 1 in shorthand. But the field phi also appears twice in the potential energy term to the right, squared and to the 4th power. And this whole thing is the potential energy of the field as a function of time and space. In other words, it can be different in different places and at different times. You can see also that the potential term depends not only on phi, but on 2 parameters, mu squared and lambda. Again, I apologize for the use of the letter mu to mean 2 entirely different things. The mu in this potential part is just a parameter or constant in the equation, which turns out to be the mass of the particle excited from the field. I could, I suppose, have used something else, but most textbooks, many textbooks, use mu, so I stayed with that. The parameter lambda is dimensionless and is known as the quartic self-coupling. It accounts for the strength of what is called the Higgs self-interaction, and it also affects the production rate of Higgs particles, pairs, in experiments. The actual values of the parameters mu and lambda are not predicted by the standard model. There's more work for us to do on Lagrangians before we get to the Higgs boson itself, but it's been said that if lambda had been known, then the mass of the Higgs boson could have been predicted before it was found. They would have known exactly the right energy to look for it in experiments. As an aside, now that the Higgs mass has been measured by experiment in 2012 to be about 125 GeV, the value of lambda, the Higgs self-coupling strength, has also been calculated, and it's been found to be about 0.12. Anyway, that's the Lagrangian for a field that only has size but no direction, a scalar field, at least as far as we've discussed it. It may grow arms and legs later, but that'll do for now. At this point, though, for completeness, I should very briefly show, without any detailed discussion, what the Lagrangians might be like for other types of field. Once I've done that, I'll come back to the scalar field and work on it towards the Higgs mechanism. This following discussion of the Lagrangians of other types of field is going to be very, very brief, just to show what they will look like, so bear with me. We look first at the Lagrangian for a free spinor half fermion, if you like, the Dirac Lagrangian. For a Dirac field with spinor half fermions, such as that for the electron field, the Lagrangian density turns out to be L equals I psi bar gamma mu delta mu psi minus m psi bar psi. Don't be put off yet. I just want you to try and appreciate this. I think you can probably see some kind of similarities to the scalar Lagrangian. What I mean is, there's a term with the electron field squared. That's the psi bar psi. And it's multiplied by mass. Okay, it's not mu squared or mass squared, it's just mass in this case. But that whole term seems to be a kind of potential energy term. There's also something that looks to be the kinetic energy of the electron field. The d mu psi gives the rate of change of the field. Okay, it's not squared as it was before, but it does represent the rate of change of the field psi. And there will be 4 terms here. It's just the way the mathematics comes out. The gamma mu thing would need explaining too. It's a special set of 4 supervectors called matrices, mu equals 0, 1, 2 and 3, and they contain mostly 1s and a few other things, but don't worry about that. I'm not saying this is simple, but if you were to play around with this Lagrangian for the Dirac field, if you were to apply Euler's equation, you would eventually get to the Dirac equation, what we would have called the equation of motion if we were in classical physics. I gamma mu del mu psi minus m psi equals 0. Though there are other ways to write it out. This is just one way to write the Dirac equation. Anyway, that's the procedure I want to emphasize. Get the Lagrangian, apply Euler's, and then interpret what comes out. Quickly moving on, what about the Lagrangian for the spin 1 vector field, such as the electromagnetic field? This is actually called a Proca Lagrangian, and it's named after a Romanian physicist, Alexander Proca. This describes a spin 1 field of mass m with, once again, the values of mu equals 0, 1, 2, and 3. Okay, it looks awful. But just note at this stage a few things about it. First of all, the equation has mass m in it, a bit like our other mu in the scalar case. I'll say that again. We're using a Lagrangian with mass in it for a spin 1 vector field, such as the electromagnetic field and photons, which we know have no mass. Don't be confused. It turns out in some cases, such as for photons, the mass will disappear. We'll eventually put it equal to 0. If you like, we're starting with a more general case. If the field was excited, it would produce a particle with mass m in this case. Once again, although this looks complicated, you should be able to see some similarities with our simpler scalar Lagrangian. Never mind the 16, the 8, and the pi's, and the fact that the positive and negative signs seem to be the wrong way round. There's a term with the field vector A squared. Remember, A is the usual symbol for the vector field, and it's multiplied by mass squared, just as before. We can surely identify that as the potential energy term. There's also a rather fussy-looking pair of subtracted derivatives which are multiplied together, effectively the derivative squared. So we also have a kind of kinetic energy term. For completeness, I should say that each of these brackets is known as the electromagnetic tensor and is usually given a shorthand, given the uppercase letter F as a shorthand. So this is really like F squared, and takes the place of our derivative squared for the kinetic energy of the vector field. In fact, we could write the Proca Lagrangian like this: minus a 16th pi f squared plus m squared over 8 pi a nu. Anyway, with this Lagrangian, if we want to focus on the electromagnetic field, we can choose a particular gauge called the Lorentz gauge, and this makes the mass equal to 0. And the term on the right disappears, giving L equal to minus 1 over 16 pi f squared, which is really L equals minus 1 over 16 pi multiplied by this funny differential subtraction squared. If we then play around with this massless Lagrangian using Euler's equation, we will eventually get to Maxwell's equations, the ones with no charge or current in them, because it's a free field. Again, I don't want to say any more about that really, except perhaps briefly to answer the following question. What about different types of fields together? We know, for instance, that electrons, which are charged particles of the Dirac psi field, interact with the electromagnetic A field, the vector field. We know that because like charges repel by the exchange of photons and unlike charges attract. So we would expect that if an electron were emitting a virtual photon because it was attracting with another charge, we would expect that the total Lagrangian for that system ought to contain things in psi for the electron bit and things in A for the exchange photon. The Lagrangian would contain both. It would represent the various energies, kinetic minus potential, when the two types of fields are together. So for interest, here's the Lagrangian density for an electron field, psi, coupled to an electromagnetic field, A, without mass, in other words, the massless photon. We could call this Lagrangian the Lagrangian of quantum electrodynamics because it involves electrons and photons. I won't read it out. You can simply look at it. Again, I don't expect for one moment it will make a great deal of sense. but we may be able to tease a few things out. There's obviously some other physics of the interaction of fields going on that we can't at this stage begin to understand, but let's try and tease out what we can. It might look strange, but let's try. I think you should be able to see that this has some similarities with what we are becoming used to for a Lagrangian, involving kinetic energy minus potential energy for fields. There's the photon field kinetic energy term in F squared, the electromagnetic tensor squared. This is related to the square of the derivative of the field A, the electromagnetic 4 potential. This has no mass term associated with it, no potential energy term, nothing else in A squared is mentioned, because obviously the photon is massless. Okay, this F squared is negative, but we'll ignore that for now. There are the two parts of the Lagrangian for the free Dirac field that we had before. One part has the electron field squared, multiplied by mass, that's the potential energy. The other is related to the kinetic energy of the electron field, involving a single derivative, the stretching of the field over space and time. Those two would be the normal free Dirac field of the electron. So we've dealt with three of the things in this Lagrangian for quantum electrodynamics. But of course it's not free. It's not a free electron, because there's some kind of interaction term in our Lagrangian. A term which actually has both fields in it, the electron field psi and the electromagnetic 4 potential A. And it's this term that explains how the electron interacts with the photon via the electric charge. In a simple way, you could say that this is what does the attraction or the repulsion of the charges. You can even see that the strength of this term is given by the multiplier E, the electric charge. We'll say a lot more about that later, much later. I want to put all this talk of Lagrangians for fields to bed now. I'll return to the scalar field example later when we come to focus on the Higgs in order to try to understand the effect it has on other particles in giving them mass. But for now, let's just leave them. Before we move on to Higgs, the first thing I'll mention is that it would seem that the kind of fields which, when disturbed, produce particles with mass are those which have a quadratic nature to their potential energy curve. Here's a typical illustration of a scalar field with its quadratic relationship. When the field phi is 0, the potential energy is at a minimum. Again, we could show this as a ball at the bottom of the valley. But when the field goes positive or negative, the potential energy increases. In a sense, this graph applies to a point in space where the field exists, and you could say that every point in space can be described by its own such graph. If we focus on one point in space, and if the field at that point is disturbed in some way, the potential energy will increase momentarily. Again, we'll draw it as a ball up the side of the cup. In this case, the field has gone positive. The field has gained energy. Of course, it won't stay there. The potential energy will want to return to the minimum, or if you like, the ball will roll down to the bottom of the hill. Once it does that, it will overshoot, and then it will oscillate backwards and forwards. Still focusing on this one point in space, we could plot the oscillation of the field against time as this imaginary ball rolls backwards and forwards. Clearly, in this kind of plotting, the time period will be as shown. This is the inverse of the frequency of the oscillation. Remember, this is the plot for a single point in space as it changes with time. But of course, we realized earlier that when a single point in a field is disturbed, it will pull other points in space along with it, like ripples in a pond. If now, instead of focusing simply on that one point, we look at points next to it in one direction, say the x direction, we can imagine that each point has its own potential energy curve. And there's our point on the left, which has had the field increased or excited. Let's assume that this point on the left has been oscillating for some time, the field value going positive and negative and the energy going up and down. And let's assume that the ball has just moved up in energy to the top of the cup and is just about ready to fall again. The adjacent point will have been disturbed by all these changes much earlier, but will be lagging behind the first one. It will be on its way up. So at this instant in time, it will be part way up. Similarly, at this instant in time, the next point in space will be lagging even further behind, perhaps passing through the zero of the field, but on its way up to the right of the diagram. And so on through space in this x direction. Now, as we look at that picture, we could plot the field as shown at these points, the right-left measurement, against distance away from the original point, and we would see that the wave, we would get a picture of the wave travelling through space. Remember, this is a photograph, this is a snapshot of a single moment. At a later time, the wave shape would have moved to the right. And of course, the measurement shown now here is the wavelength. I'm sure you realize that this is simply an illustration of the way in which a wave or particle emanates in one direction from a point where the field has been disturbed. The earlier illustration we gave was of a pond being disturbed, a water surface being disturbed, where the wave was shown travelling in all directions. Of course, in any disturbance in a field like this, there is 3 dimensions, and one has to ask how an excited particle can only travel in one direction. Well, that is something for quantum mechanics to try and answer, but we'll leave it at that for now. The other thing I wanted to clear up before the next session, where we'll start to focus on the Higgs field in more detail, is something to do with the vector field. Remember, vector fields are the fields that describe the gauge bosons. We have the photon vector field, the gluon vector field, and the W and Z boson vector fields. These are the force carriers, or the gauge bosons, of the Standard Model. I have said that the Standard Model insists that all the particles excited from these fields must have zero mass, even though we know from experiment that the W and Z don't have zero mass. So why does the Standard Model insist on this zero mass requirement for all the gauge bosons? Here's my question. Why does the Standard Model insist that gauge bosons have to be described mathematically by field equations and Lagrangians for massless particles? Well, the answer is all to do with gauge invariance. And as I say, this idea applies to all 4 types of gauge bosons, the gluon, the photon, the W and the Z, although I'll illustrate it in connection with the photon field A. As we said before, a general feature of field theories is that the fundamental fields, the underlying fields, cannot be directly measured. However, there are observable quantities that can be calculated from the underlying fields and that can be measured experimentally, things such as charge, energy, magnetic field, velocity, and so on. And perhaps a simple example to discuss is the one given earlier, the electromagnetic field. The actual field is called the electromagnetic 4 potential and given this letter A, but it cannot be directly detected or measured. However, using mathematics, in particular one form of Maxwell's equations, the measurable magnetic and electric fields B and E can be shown to be related to A by the following equations. As I said before, for those who are not familiar, these equations are saying that the magnetic field B is a particular type of differential of A, and the electric field E depends not only on the differential of the voltage with respect to distance, but also on the rate of change of the field A with time. That's fine. But on top of that, in field theories, different values of those underlying fields can end up giving you exactly the same measured quantities for things that we measured in the laboratory. In other words, you can change the field A by certain amounts, and from the mathematics get exactly the same answers for the magnetic and electric fields B and E that you had before. As we said earlier, such a transformation from one value of the underlying field to another is called a gauge transformation. The gauge field is changed to something different, but the measurable quantities stay the same. They are invariant. They don't change. And we call the property that the field has which allows it to behave like this gauge invariance. Any kind of invariance under a field transformation like this is considered to be a kind of symmetry, so the gauge invariance sometimes is called gauge symmetry. Generally, any theory that has the property of gauge invariance is considered a gauge theory. So in physics, we say that a gauge theory is a type of field theory in which the Lagrangian doesn't change or is invariant for a continuous group of local transformations of the field. That will mean that the measurable quantities will be unchanged, even though the underlying field may have changed. For this, the Lagrangian must be invariant under some symmetry transformation groups. I don't know whether you noticed that I introduced the word local into that last statement. I said, a gauge theory is a type of field theory in which the Lagrangian doesn't change or is invariant for a continuous group of local transformations. If I was simply to transform the field A by a constant amount everywhere in space, that wouldn't be particularly local. And even though the measured quantity stayed the same, we could only say that the underlying field had global symmetry. Global because everywhere had been changed by the same amount. But that's not enough for gauge invariance. In order to be called gauge invariant, we need to have the much more strict constraint, which we call local symmetry. That means, for a field to satisfy a gauge theory, it must be invariant to changes in the underlying field which vary in some way from place to place or from time to time. They're not the same changes everywhere. They're not simply global. The changes to the underlying field have to be allowed to change by different amounts in different places and different times. I don't mean they vary haphazardly, but in a predictable way according to some kind of function. So the change may be different at different positions in space or at different times, but those changes would be predictable in terms of some function or other of space-time. Let's consider a free spin 1 vector field which I'll call A mu. At this stage I don't necessarily mean an electromagnetic field, I mean any vector field, the excited particles of which could have mass. So as yet I'm not talking about photons. It could be any of the gauge bosons in the standard model, and we'll assume at this stage that they could have mass. I now want to think about transforming that vector field A mu by adding something to it that depends on space-time, on t, x, y and z, and seeing if A is invariant or whether I can fudge it to be invariant. First of all, I need to invent something to add which will be different at different times and different places in a predictable way. And a good example, something we looked at before, would be to start with some scalar function, say alpha, which varies with space and time. Alpha is a function of t, x, y and z. Now this isn't what we're going to add, but we'll start with this. Now because we have a new kind of shorthand, we can write this as alpha of x mu, where mu takes on values 0, 1, 2 and 3. If we then take the derivative of this with respect to space-time, it will give us 4 terms in t, x, y and z, but we can write those 4 terms as d alpha by the x mu. On top of that, our shorthand for this could even go less. We could write it as d mu of alpha. This derivative, don't forget it has 4 terms, could then be the thing that we add to a mu. Then, providing alpha varied with x mu in some way, we know that the 4 parts of this derivative, the alpha by the x mu, are definitely not constant everywhere, and we will be adding different things to different places or different times. We know that it would not be simply a global transformation, but would be a local transformation. So we're going to assume that in adding d alpha by the x mu, we are to our underlying field, we are adding something that can depend on x mu, on space-time. It's different everywhere. It's a local transformation. Here goes. The action of this particular gauge transformation on the gauge field means that a mu changes to a mu plus d mu alpha. Or if we leave out the mu index for simplicity, a changes to a plus d alpha, where the alpha is still the 4 terms in time x, y and z. But remember also a has 4 parts to it as well, so the bits will add up sensibly. Now you may recall that the Lagrangian for the vector boson was the Proctor Lagrangian. Okay, it's messy, I know, but bear with me. That can be written as minus 1 over 16 pi f squared plus m squared over 8 pi a mu. So the question, does this change if I make this local transformation on A? Does this L change? A quick and easy way to check this is just to look at the mass term and see if it changes. The mass term, ignoring the a pi and the mu index, is simply m squared a squared. So if I take the Lagrangian of the mass term, I can write down in my shorthand m squared a squared. So let's see how this mass term of the Lagrangian will change when we make this substitution for a. A goes to a plus d alpha, again using the new shorthand. Will the mass term with a plus d alpha in it be any different from the mass term with just a in it? If it's gauge invariant, it won't be any different. Putting this a plus d alpha into the mass term, it then becomes m squared into a plus d alpha times a plus d alpha. Expanding this gives me the terms m squared a squared plus 2m squared a d alpha plus m squared d alpha all squared. Now we were hoping for invariance, that this would be the same as before, m squared a squared. But we have 2 extra terms. Fortunately, we can ignore the second of these right away. This is simply some kind of extra kinetic energy. We recognize that from the d mu alpha squared, or d alpha squared in my shorthand. We can ignore it because it would simply contribute to the kinetic energy, and it in no way would affect the mass of any excited particle. So for our discussion, and thinking about whether the mass term has changed under this transformation, we now need to look at Lagrangian of the mass term is m squared a squared plus 2m squared a d alpha after we substituted this new a into the Lagrangian. There's the original mass term, and the action of the gauge symmetry changing a mu has had the effect on the mass term of adding something to it. But we said that for gauge symmetry, the mass term in the Lagrangian must remain the same. The mass, after all, is a measurable quantity, and the whole point is that measurable quantities don't change even if the underlying field a mu does change. So if you look at that extra expression for the mass term, the only way we can make it as it was, that extra bit has to be 0. 2m squared a d alpha must be 0. How can that be? Well, we have 3 possibilities. Either d alpha, d mu alpha must be 0. Well, we can't have that because that would mean we will be adding nothing. Secondly, a could be 0. Well, that means the underlying field is 0, and is always zero. There's no excitations, no particles. A has to be zero. That can't be true. The only other possibility is that the mass of any excited particle must be zero. The mass of the gauge boson must be zero. That is the only sensible possibility. Therefore, at this theoretical level, all gauge bosons of spin 1, vector bosons, must be massless. And that means the forces that they describe must be long-ranged. It also means that all the vector bosons in the standard model, the photons, the electromagnetic field, the gluons of the color field, the W and the Z bosons from the weak field, according to the theory, all must be massless. They all should have zero mass according to the standard model. The other arguments for this, some people suggest that you have to think about the number of polarizations a field can have, and the fact that if a boson has zero mass, it can't be longitudinally polarized and so on. That might come up later, but for now I hope it seems reasonable that all the bosons of the standard model really ought to have zero mass for the Lagrangian to be invariant. And the point is, of course, that they don't. They don't all have zero mass. The W and the Z bosons have quite high masses, resulting in the weak force being just that, weak. Which also means their range is short, because in low energy situations where there's no spare energy around, they have to borrow large amounts of energy from the vacuum in order for them to be created, so that interactions can take place. So that the force can be felt, if you like. This large amount of energy has to be paid back quickly, and hence the particle can't travel very far before it decays, and that means the force is short range. Anyway, now that we've answered the question as to why the standard model insists that all gauge bosons should have zero mass, we can start to think about why some of them actually don't have zero mass, namely the W and the Z bosons of the weak field. And in the next part we will return to the scalar field, and in particular to the Higgs field, in order to try to explain how the W and Z bosons obtain their mass via the Higgs mechanism.